Cool. So the basic idea of machine learning is that you have we'll talk a little bit and we'll see some examples about the specific kinds of problems that are amenable to machine learning. It's one approach. It's one approach among many. So we learned about object-oriented programming and functional programming and stuff like that. So this is, I wouldn't say it's another style exactly, but it's an approach to programming that is good for certain kinds of problems. And you can basically think of a machine learning model as a function, but it's a function that you don't directly write. So it's a function that takes some input and it gives you some output. So you give it something and it gives you something back, just like a normal function. So if I want to have a machine learning model that, ChatGPT or something like that. So this is more sophisticated, but it's the same basic idea. Whereas you give it a prompt, right? You give it some input, some text input or whatever, and it gives you back something, gives you back some more text. So it takes a string and it returns a string. The hard part or what's actually happening inside of that function, what's different about machine learning is that you don't directly write the code inside of the function. So instead of normally when you write code and you say, okay, I want to do this, and then you write everything that you want the function to do, and you tell it what to return, and then that's it. With machine learning, you supply basically it's like a class or something where you have a template, so like an algorithm, and there are different kinds of algorithms that you don't really need to know the details of them, but they're available in libraries, which we'll see in a second. But you kind of choose the template you want to use, and then you give it a bunch of training data. And the training data, when the model trains itself, it's kind of like building its own internals of the function. So it's deciding what's going to happen given certain kinds of inputs. And when you're done training, you have basically the function written. You don't have direct access to that function. You can't really see what's going on most of the time. Sometimes you can, but that's the basic idea. It's just you're creating a function based on the inputs. So the only direct control you have over how your function works is the inputs that you give it. And so contrary to what you might think if you don't really know anything about machine learning is almost all of the work is getting the inputs to be right, choosing correct inputs, modifying those inputs, and so on. So it's really all about inputs. Once you have your inputs all lined up, the actual machine learning part is kind of just a throwaway. You just do it and that's it. So the hard part, all of the work, all of the thinking really occurs before you give your inputs, your training inputs to the model. All right, so there's a README here. I think I'll kind of loosely just go through it. And then what I really care about is these couple of examples that we'll see after this. So here is a problem that humans can very easily solve, right? We're very good at things like this. You see a 0, and then you know that this is a 0. You haven't seen a 0 that's exactly like this before, just like, speech. For example, speech, like you haven't heard someone say the word cow exactly that way. If you were very precise and measured all of the frequencies and the whatever other things you can measure, you would find that you'd never heard any chunk of sound that was exactly like that, but you still identify it. So you're able to kind of generalize, right? Humans are able to take a limited sample of data and generalize to unseen examples. And that's really what you want a machine learning algorithm to do. You want to give it a bunch of examples and then have it generalize and perform well on examples that it hasn't seen before, but that are similar to examples it's been trained on. So that we have here, so humans are good at this. This is not a problem. So the real hard part here is, how do we take, for example, an image and turn it into something that we can use in a programming language like Python? So here is an example of a 1, and what this is indicating is that we can kind of represent an image as a grid, and we can represent a grid as a multi-dimensional array, so as an array of arrays. And there's there isn't just one way to do this, but so we can have elements, we can kind of divide this up into grids, and the grids may be arbitrary. We may want very fine-grained detail. We may not need that much detail. We could have break this into larger chunks or smaller chunks, but however we do that, we can kind of say like, okay, here's an element, 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 and we can go down and do that, and we can represent, for example, the black space with zeros and the white space with ones. It doesn't really matter what you choose. It could be true, false, or an X or a Y or whatever. But we can simplify this down into something which is a multi-dimensional array, and then for any given, let's say, row, column, it's either there's something there or there isn't something there. It's possible to do more refined things, like maybe here it's not just black or white, it's kind of gray. So you might have multiple values. That's also possible. But the general picture is that we have something in the real world that we want to represent to a computer, and in our case, Python. So we need to think about how we could transform some real world object into a Python object. So here's another example, another way of doing this. So any guesses as to what this letter could be?
A period.
It could be a period, yeah. I mean,
I just got that because there's one single value in there, and it's the first one. So if you look at it in grid format, like the one above it, right? I don't know, just grasping.
sure, yeah. That's good. So grasping is fine. So this is somewhat arbitrary, but if I told you that so this is a somewhat arbitrary representation of an image, right? Like there's potentially lots of ways to do it, but this is one of them. So this is kind of a symbol or a representation or a translation of some real world object. In this case, like, a picture of a digit. This, if I tell you that this is a letter, so it's one of the letters of the alphabet.
A?
Yeah. So it could be anything, right? It could be anything, but there are 26 values here, which, I don't expect anyone to count that, but there are 26, and one of them is like on. So these are all kind of offs, and then this one is an on. And a B, you might represent it as 0, 1, 0, 0, 0, 0, 0. So this is something that's called one-hot encoding. So this is a common way to represent text, actually. So anything you give to a machine learning model essentially has to be an array of numbers. So that's ultimately your goal is whatever input you have to figure out a way to turn it into an array of numbers. And ideally, an array of either ones or zeros. Sometimes other things, and that's fine. That, you know, there are definitely more sophisticated and complicated and other ways of doing it, but this is the basic idea. So we take a letter, right? A letter is just A. So, you know, we can represent strings, that's fine. But what we really want for a machine learning model input is an array of digits. And we could do the same thing with like the dictionary. So here's a letter. So our kind of domain is, if we assume only lowercase, you know, English ASCII characters, there are 26. What if we don't want to represent letters, but we want to represent English words? Well, then we could either use the entire dictionary and create an array which is the length of the entire dictionary, and then, you know, aardvark or whatever the first word is would be 1, and then you'd have, like, I don't know, 300,000 zeros after that. And so every word could be represented. Every word in a dictionary could be represented this way. So you can apply this basic idea to lots of domains. Sometimes it's, you know, hard to do. It's not obvious, but there's usually a way to kind of make it work. Okay. So let's say that we've, you know, taken, we now have our like real world object we want to ask a question about, and we've turned it into something that, you know, Python can understand, like a list of digits. So now if we want to write a function that will like tell us what the digit is, we might imagine doing something like this. Right. So this is the, let's say, traditional approach to programming, is where we're basically like telling it what we want to do. So if it's this, then we know it's a 1. And then we can expand that and say, well, you know, there are lots of, this isn't the only possible representation of a 1, right? It could be vertical, it could be a little bit to the left, it could be shorter or longer or whatever. So there's all kinds of possible variations of a 1. So this is where it basically becomes impractical to solve this problem using traditional a traditional approach to programming, where if we hard code this, you know, we could potentially be very precise, but even with this 5x5 grid, you know, it would take, you know, hours to code up every possible variation of all 9 digits. And that's a very limited domain. It's a very limited domain, and it still would just be like tedious beyond belief. And then if there were any bugs, like, you know, it would just be a huge mess. So this is not the way you want to solve it. What you want to do instead is use a machine learning model, and all of the guts in here you don't care about. You just give it the model, and the model takes care of all the garbage, and you don't have to look at it. Doesn't matter how ugly it is inside, it's sealed up in a box, so you don't have to worry about it. Any questions so far? Okay. So here is a link to, so there are a number of different libraries. I think this one is it's very good in Python. It's easy to use. The documentation is good. So this is what I would recommend when you're learning. There's obviously like more advanced, complicated stuff, but yeah, it's just not worth it at this point. And you can see here that the documentation kind of starts you off with, you have classification, regression, and clustering. And these 3 categories are the basic kinds of machine learning problems that you can have. So classification, so just based on the name, what kind of problem is identifying a digit? Is it classification? Feel free to guess. Classification, regression, or clustering?
Classification.
Yeah. Yeah, it's classification because we have our inputs and our outputs are kind of known, right? We know in advance that it's either going to be a 1 or 2 or 3 or 4 or 5 or 9, right? So there's a limited number of buckets that we expect as outputs. So whatever we give it as an input, we want it to put in one of those buckets. So this is good for, something like spam, like a spam filter. That's going to be a classification model. So, if someone sends you an email and you're, an email hosting service or whatever, you want to filter out spam. So you're going to have some kind of machine learning model, which is trained on identifying, is this spam or is this not spam? And so every email that comes through is going to fit into one of those categories. Now, in the real world, obviously, there are edge cases and blah, blah, blah. But, the basic problem is one of two things. It's either spam or it's not spam. The other common kind of problem is regression. And regression is when a regression kind of problem is when your output is not going to be like a finite or discrete value. It could be anything. So like forecasting the price of a stock or housing prices or stuff like that, where it could be kind of anything. So you have like a line, like a trend line or something like that. So that's what you're trying to represent. Now you can't, I don't want to confuse you, but you can kind of transform a regression problem into a classification problem. So for example, if you're interested in predicting stock prices, but you really only care, like, did it go up or did it go down? Then you can take that and make it a classification problem. So there are, these categories are not like absolutely strict, but in general, that's how it works. And clustering is related. So it'll look at data and then group things together. So things which are, strongly related to other things. So you give it features, for example, like topic modeling. This is a common kind of clustering. You feed a whole bunch of text into a model and you say, like, how could I cluster all of this text into smaller groups? Like, okay, here's a text about, science, and here's another text about literature, and here's another text about whatever. So that's clustering. Well, all the examples I'm going to show you are classification examples. All right, any question about that? Okay, so I'm just going to show, I'll click in here, and this can be very intimidating. You have all this very math heavy stuff, and look at just lists and lists of stuff, and it's very overwhelming. So you don't need, I know almost nothing about mathematics, and I can still use this stuff. So, don't feel like you have to be an expert in statistics or math to use this stuff, because you don't. So here are a bunch of models: linear, quadratic, blah, blah, blah. So nearest neighbors. So there's a whole bunch of models that you can choose. I'm going to focus on this. So we're actually going to use naive Bayes and decision trees in the examples. So these are good places to start. There are all kinds of different models, and if you're actually doing something, it's pretty easy with scikit-learn, especially if you're not doing some like, crazy billions of samples data set. It's easy to train lots of different models. You can train lots of different models and just see what works better. So yeah. And then so I'll just click into decision trees here, and this will usually give you some kind of background, technical background, and then there's a basic example. So this is not going to make a whole lot of sense to you right now, but hopefully it will shortly. So we have an X. So this is an unfortunate, I think, convention in machine learning where you use X and Y for your input data, and then Y would be the labels. So for example, in this example of this numbers, so your input would be, all this junk, the kind of transformed representation of the thing that you're interested in. So that would be this right here, that would be X, and Y would be whether or not it's a 1 or 2 or 3 or 4 or 5 or whatever. So this is Y's would be the corresponding labels. So this first thing would be a representation of some real world object, and this would be the the category label that it belongs to. So this would be for training data. So for training data, for supervised learning, you need to know what the thing is and what its value is. And then all you do really is this. You just create an instance of the class, and then you call fit on it and pass it this, and it trains the model. And you don't need to worry about it. And then once it's trained, you can test it out. You can see how it performs on novel data, and then you can make a decision about, okay, should I retrain this? Should I choose a different model? Should I modify my inputs, and so on? Okay. Yeah, I think I can skip this. Yeah, okay. So anyway, I'm gonna go ahead and move on to this short walkthrough here. Are there any questions before I do that? Any questions about the basic idea of what machine learning is? Okay. All right, so here is an example. I'm going to clone this down. Let me do. Okay.
Chad, I just have a quick question.
Yeah.
I noticed you went with decision trees, and I remember when I was studying all this, we would have to do like at the final project, we were doing a bunch of different models, testing testing the errors to see which was the most accurate. And always decision trees kind of was always head and shoulders. Is that why you went that way? Is it still kind of the convention that decision trees are still kind of the cream of the crop?
So you can actually get kind of complicated with decision trees. So this is just a simple, they're actually you can kind of do decision trees on top of decision trees. So yeah, I mean, the basic reason I chose it is because it's pretty simple to understand, and it comes with an easy way to represent the internals, which we'll see in a second. So you can actually kind of see what it's doing. Whereas with the other models, it's a lot harder to kind of like see what is actually happening internally.
I see what you're saying. Okay. This is you just chose it so we could see the inside of the black box a little bit better.
Yeah.
Okay.
Yeah. It's basically, I think it's conceptually the most familiar to what we already know. But yeah, I mean, so it's also just true that, there's all kinds of like super fancy high-end models and stuff, but like, the simplest stuff also works very well.
Yeah, the guy that kind of was very involved in all this, his name was Clive Granger, if I remember right. He won a Nobel Prize for exactly that. All these models, all your probably your deterministic models, he came up and he won a Nobel Prize for just saying that go with the simplest thing. That usually is what works in the end. And he got a Nobel Prize for that.
Yeah. yeah, there's definitely something to be said. Like, why not solve the problem in the simplest possible way? There's also, people like to do the coolest new thing, and people like complicated things because it's, an intellectual challenge and all that stuff. But from a practical perspective, yeah, it makes sense to just use the simplest, the simplest thing that basically works. So,
Thank you. That helps. That now I know it's basically the same as it used to be. Cool. Thank you.
yeah, and um, a, a lot of what counts as like, is this model good or is it useful for my application, is going to be specific to your application's needs. So for example, if I were, I don't know, if I were training a model on like, should, uh, you know, should patients get some risky surgical procedure or not? I would want that model to be like really accurate. I would want it to be in the like, upper 90s at least. If it's like 70% accurate, is that, is that good? Is that better than not using the model? Maybe, maybe not. Something that's lower stakes, or maybe that doesn't really matter that much. Like, you know, you might be willing to accept different ranges of accuracies, and in the context of how would we solve this without a machine learning model? Is it better than that? Is it good enough? Could we use a machine learning model but then wrap it in some kind of caveat or whatever? So yeah. Okay, cool. So I want to not throw new things at you, but there's a couple new things that I will throw at you. It shouldn't be too bad. One is Jupyter Notebook. So that's basically it for this. So we're gonna have to use Jupyter Notebooks just because it makes everything so much easier. Okay, so first thing I'm gonna do is I have this requirements, which is pretty beefy because I'm using Jupyter. But I have that there, so I'm gonna create a virtual environment, pip what? Oh, sorry. Yeah, thank you. And then I'll activate it. Okay, so I'm going to install the requirements. And we'll take a look quickly at the problem. So this is an example. It's a contrived example with dummy data that I'm just generating. But let's say we have a problem. We're running a restaurant and we want to determine, what temperature do we keep the restaurant? So we want to minimize, let's say, complaints or something like that. And so we can formulate this as a classification problem. So let's say you have data, you actually have data, you have records of like, complaints, customer complaints with corresponding temperature when they complained, something like that. So obviously you can try it, but let's just, roll with it for now. And so you have all that data. Let's say you just have it on like cards or slips or whatever. And so you enter that into an Excel spreadsheet or something like that. So the whole data processing, finding the data that you need, making sure that it exists, and then putting it into a format that you can consume is its own problem. Actually, let me show you. Okay, so there are a few different places you can kind of go to get data. Kaggle is one. Oh yeah, there's the datasets link. So Kaggle is kind of like it's one of these like code competition sites where they have contests, but it's all basically like machine learning contests. So they'll give you a data set. I think a lot of times like companies will have a problem and then they'll offer a prize for the best solution, things like that. So if you want to play around it, it's a little more advanced, but this exists. And one great thing that you can use immediately is these data sets. So I can look for one. either computer vision or NLP, natural language processing. So I like that stuff, so I'll click on that. Chatbot data set. So for example, we can take a look at this real quick. So here's an example. This happens to be in JSON, but it could be in, CSV is probably the most common format that you'll see data sets in. This is in JSON. So this is training data for a chatbot. So something like greeting. So there's a general category called greeting. And here are a bunch of training samples like, hi, how are you? Is anyone there? Hello, et cetera, et cetera. So this is training data. This is training data, and it's associated with this tag of greeting. So if I'm training a chatbot, the user gives it input, that's input to the function, and the chatbot gives output, which is the return value of the function. So if I give it, input, the model should be trained, and it should be able to identify if someone says hello or something like hello, that, okay, this gets the label of greeting, and then when I have greeting, I give X response. So that's the basic idea. You can play around. So, figuring out what your problem is and figuring out if there's a data set available, and then taking that data, and usually you have to do some kind of transformation and processing to get it to be in a format that you need. So that's the basic hard part of this. Okay, so let's just say, for example, that we can kind of skip some of the hard part. We have our data, and it's in a CSV file. So now that I've got that, should be installed. So I'm gonna run this notebook right here. And Jupyter will spin up like a little local server, and then you can view your code here. So a couple nice things about Jupyter Notebooks is you can run both Python, and then you can also have Markdown. So you can kind of like explain what your code is doing and then write a little chunk of code and then go on. So Jupyter Notebooks, for those who haven't been exposed to it, it's kind of like a hybrid between just writing code here in a file and then running it, which is what we usually do. And if I just go Python, I can go into the interpreter and just do something quick. So 3 times 4, and I get an answer, right? So if I just want to try out like a thing real quick, like, oh wait, does this list method do what I think it does, or whatever, you can just pop open an interpreter and do something real quick and then close it. So it's, it's very easy to do quick things. So you have this on the one hand, then you have this on the other hand, and Jupyter is in between those two things. So it allows you to write code in a cell, like a little block. You can run it, and then it kind of like stops. So everything that you have, if you create any variable names or anything like that, if I import stuff, it will save. So anything below it, anything that you run after will have access to it. But you can also like rerun stuff. So if I run something and it doesn't work, I can make a change and then run it again and then move on to the next one. So this is really useful with machine learning because, as with all programming, it's an iterative process. But a lot of the things you do, are potentially time consuming depending on how much data you're processing. So you don't want to have to constantly, if an entire processing pipeline takes, let's just say you're doing local development, it takes 10 minutes to run or 5 minutes to run. As you're developing, you don't want to have to wait like, okay, I'm going to make one small change and then run it and wait 5 minutes to see what happens, and then and so on. So this just makes things easier. All right, so to run this, to run a cell, you can click run up there. So if I've installed everything correctly, this should be fine. This is an asterisk while it's running, and then when it finishes, it should change. The first time it might take like a little bit to get set up. And then if you're working on this, you can change what the cell type is. So here, this is a markdown type. So I can go here to cell and cell type, and then code. This will be Python markdown. That's what this is. So I can click on this and then markdown, use 2 pound signs. This is like an H2 tag, basically. And you can press enter here to run it. Whoops. The shortcut, instead of pressing run, is shift return. But so that's what I'll be doing, but you can just click here to run a cell, or you can do shift return for the shortcut. Okay, so this is completed now. So that's all imported. Now what I'm going to do is I'm going to run this, and we'll take a look at the data that we have. So I just use normal Python here. I'm opening this raw data.csv. So we're pretending that we've, this is our starting point. So here that is CSV data. It's got 2 columns. It's got a response, which is we've categorized into one of 3 possible values, and then the temperature. Then we're doing is we're just reading in like we've done many, many times. And then here I can just kind of I don't have to call print explicitly. The notebook will automatically pick up that I want to print this if it's the last thing. Okay, so here's our representation. So we're taking this CSV data, which we've already transformed and processed, and turning it into a bunch of arrays. So here we have our problem, or this is the category that we want. So we're expecting an answer to be one of 3 things, either too cold, blah, blah, blah. And here's our input data. Now you could have, in this case, we just have a single value, but you could have lots of other things, like we saw in this example, where you have potentially, very, very complicated things, or if you're trying to guess a letter, it might look like something like this or whatever. Okay, so we got this, and here so here's what I used to generate all of the dummy data. So if you want to run that, you can. All right. So once we have the data, we'll notice that this is text. So this is good. It could be better. We could do something with that, but we're just gonna leave it at that. It's a number, so it's good enough. This, however, is not good enough. Our machine learning model doesn't know what to do with strings. So we're gonna have to turn this text into a number. And luckily, it's fairly straightforward. So here's a dictionary that could do that. So if it's too hot, we'll make it a 1. If it's just right, we'll make it a 2. If it's too cold, we'll make it a 3. So this is arbitrary. There's no inherent connection between 1 and being too hot, or 3 and being too cold. It's just arbitrary, as long as we remember how to convert that, because our model is going to spit out a number. Ultimately, it's going to take in a bunch of the numbers. It's going to take in a list of numbers, and it's going to return a number, basically. Okay, so we'll go ahead and do some more data processing. And you can see that here. So here's our process data. So we started with, too cold, 57, and we want to end up with 357. And we know that 3, we can map 3 to the string too cold. So this is, at this point, our machine learning model is pretty happy. It likes this kind of stuff, but we have no idea what's happening, basically. Right? If you hadn't gone through this process yourself, and we're tracking everything, this would just look like, a random list of numbers or whatever. So this is, it's just one of the difficulties of machine learning, but you just have to kind of keep this in mind. we're taking things that we're familiar with from our problem domain and our experience, and we're translating it into numbers or lists of numbers. Okay. So now that we have all of our data and it's basically consumable by a model, what we have to do is create a training and test split. So strictly speaking, you don't have to do this, but you should always do this. So there's a temptation to say, I want my model to have as much data as possible, right? The more data you give the model, the better it's going to be, right? If I have a character, an optical character recognition machine learning algorithm or whatever, and I just give it like 3 or 4 examples, it's not gonna do very well. But if I give it, millions of examples of ones, for example, it should be really good at identifying ones. If I give it billions, it should be even better, and so on. So there's a point of diminishing returns, but basically the more input data, the more training data it gets, the better it's going to be. However, so you want to give it as much data as possible. However, you also want to make sure that that your model is not overfitted. So this is a problem you can have where your model is too good. So if you're training a model and you're getting like 100% accuracy, or it appears that you're getting 100% accuracy, you should be a little suspicious. So one way you can avoid doing that, or at least you can get some insight into whether or not that's happening, is using a train test split. So what you do is you take all of your input source data that you want to use to train the model, and you just exclude part of it, usually like 20 or 30%. You just don't train the model on 30% of the data. So you take all of your data and you exclude 30% of it. Then you train the model on 70%. And then once the model is trained, you take that other data that the model hasn't seen yet, but comes from your basic source data, and then you test it, and you see how accurate it is. So that's basically how you would know if your model is doing well. And this is, this looks pretty busy, but it's really not doing very much. It's taking all of this input data, and it's just basically dividing it up into, two different buckets for testing samples and training samples. And then one further thing that you will end up doing. So here we're splitting the data just like 80% in one bucket, 20% into another bucket. But here we're doing a further division, and each one of these buckets, training and testing, is going to have a train X and a train Y. And this goes back to that kind of confusing convention that I talked about. So X is going to be just the domain that we're interested in. So just the temperature in our case. So we want to go from temperature to complaint. So here are all the temperatures, and here are all the complaints. So we need to separate that out. So the model, as it's running, it's basically just how the input has to be formatted for these models. So we're gonna take out. So we have these pairs, which are like the correct label and the temperature, but we want to like pull all these out separately. So we're going to create parallel arrays where we have a bunch of just the temperatures and then a bunch of just the correct labels.
Chad, can we think of like the X's as being like the independent variables and the Y as being the dependent variables? I mean, is it all based in statistics? Is that why they're using the X and the Y?
Yeah, so I'm not a statistics guy, but machine learning is basically just statistics. It's yes. So I'm sure that stuff is motivated from the domain of statistics, but someone who's not already familiar with that convention, it seems, you know,
Pretty out there. Yeah, I can totally get it.
okay. And then I'm going to add another cell here. So I can go to this plus sign and add another cell below, just so we can see an example of train X. So this is just the temperatures. And then train Y is just the label. So, you know, too cold or too hot, whatever it is. Okay. All right. So now that we have all of our data and it's packaged up and ready to go, we can train it. So we should have, you know, X will be like our train X and Y will be like our test Y. So all we really have to do is create an instance of whatever model we want to use and then fit it to our training data. So we'll just take a look again, kind of showed you this, but train X, so this is the temperatures, Y, this is the labels that we eventually will want the model to output, but for now we're telling it what they are so it can learn. Okay. So one other thing to note is that the inputs it has to be an array. So each sample has to be an array. So you're giving it a two-dimensional array. So even though we only have one sample here, it still has to be an array. But we could potentially have, you know, lots and lots of different features. Okay. So I'm gonna call this right here. So we don't have that much data, so it trained pretty quickly. But in the real world, you know, you might spin up like a cluster of 100 very powerful machines and run it for hours and hours and hours. Okay, so now that we have our model trained, we can test its accuracy. We can test its accuracy based on this test sample. So we excluded this stuff from the training data, so it hasn't seen this stuff yet. So we're going to run it, and we're going to get the score. So this is a pretty simple problem, and the data is all dummy data, etc. So this is a pretty reasonable expectation. If you're getting, you know, accuracy scores in the 90s, either you're doing a very good job, or your problem is very simple, or you're overfitting. And how do you know which category you belong to? Well, you kind of have to play around with it and experiment. But so I'm going to say that this score looks, you know, reasonable. It looks like what I would expect, and it is good enough. Okay. So now that I have a trained model and I can see that its accuracy is like meets my needs, I can go ahead and test it out on something that it hasn't seen. So I didn't really show you this, but if you look at the training data, the maximum temperature it will get is 100. So the model hasn't seen any temperatures over 100. So what happens when I give it something that it hasn't seen? So it hasn't seen 105. 105 is similar to stuff that it has seen. So will it do a good job of predicting this? So we can run this, and it ultimately will spit out too hot. So in this case, it gave the right answer. Even though it's never seen 105 before, it was able to correctly categorize this. So the input, remember, just has to be a two-dimensional list, and then you call predict on the model. This is just, you know, for free. All you have to do is pass it the input that's formatted correctly, and then it will give you just a number, right? Because it's just been trained on spitting out a 1 or a 2 or a 3. But then we just look at this conversion dictionary, which is over here. And so we can easily translate that from 1 to 2 hot in this example. And then again, part of the reason I picked this is because it has this cool feature where it will actually give you it gives you insight into how it's structured internally. So this is just a bunch of if statements, right? And if we had to write this ourselves, it would just be spaghetti, right? So if we have someone else do it, we don't have to worry about it. But imagine doing this like if blah blah blah, then this, if this, and if this, and if this, then this. It would just be a huge mess. So we don't have to do that. So it starts basically at 71.5, or this might be 72, since we don't give it floats. But basically, it's saying if the input, again, the temperature is less than 71.5, then we're going to go down this route. If it's greater than that, we're going to go down this route, and so on and so on. So that's the basic idea. Any comments or questions? So you can run this and play around with it. You can try it on different models, see what happens.
And I didn't just catch, how do we set up the notebook? Is that something that's pretty easy to do? Can you just find that online? Or is that in the...
Yeah, so the README will tell you. All you have to do is,
Okay, I didn't catch that.
install the requirements. You just do Jupyter Notebook, and if you just call this by itself, it will you'll be able to create files and so on if you want to. But if you call it with a file, it'll just open that directly. All right, so now I'm going to try and quickly walk through a complete deployed or complete web application that uses this. So here's the README. It kind of talks a little bit about what's happening, but basically, so this uses React on the front end, uses Django REST framework on the back end, and there's a Postgres database, and it's set up just like the Docker Compose example, where we're using Docker Compose, so it will spin up all these containers, blah, blah, blah. So you can run it locally just by doing this. So if you want to play around with it, feel free. And I have it deployed right now, which should be, I haven't checked yet. Let me see if I can go there. Okay. So you'll have to pardon my CSS, etc. But the way this works is, let me post this link in the channel here. I did this for a couple reasons. One is I used, I'm using the basic format that I showed you guys for Docker Compose, so it's easy to run locally and then deploy. And then I also used authentication. People are having issues with that. So here's the code here, the front end code. I'll just introduce quickly. So app.js, it uses the hash router. It's got a couple things. So I should say what this actually is. This is, you can draw an X or an O, and then you guess. So that's basically it. So you draw an X or you draw an O, and you train the model, and it can hopefully guess what you drew. Okay, so and then we can look here in the different components. So here's the guess component. I'm using a third-party library, React Sketch Canvas, to do this. So I don't want to go into all the React stuff. It's not, it's not the best. It could use some love, but it's good enough for an example. And the back end is what I really care about here. And here's the project level. And then in API stuff, we've got views. And we've got three basic views. We have processing, sampling, and updating the model. So the way this works basically is you provided a bunch of training data. So I'll have you guys do that in a minute. You provided a bunch of training data, and then once there's a sufficient amount of training data, then someone can log in and update the model, and internally all of that training data is saved to the database. So I had to use an array field, which is not great, but for our case it'll be fine. So I'm using an array field to save the training data, which has been processed. And then when I want to train the model, I'm also saving the model itself. So I'm saving it as a binary field. We go to the views here. So let's say the sample endpoint. So when someone gives a sample, which is drawing X and then clicking guess, or actually that will be training. So draw an X and then click train X. That request is going to go here. It's going to take that raw data, which is I should show you what that is, but yeah, I should have. Anyway, if you run it locally, you can console log what that data actually is. It's basically like XY, a whole bunch of XY coordinates that are floats. And a lot of the processing is taking those coordinates and just compressing them into smaller buckets. So instead of 34.85 blah 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 blah, it's just going to be a number between 1 and 10 because that's good enough for our purposes. So we'll transform raw line data. So we're just going to take all this data and transform it and turn it into something that's useful, which is just going to be a list of numbers. So yeah, I'm going to try to get through this quickly, but just so you can, we'll just walk through the example, and then you guys can ask if there are any questions. You can do that. So if everyone could go to this URL, you can all help me train the model. So go to that URL. Let me know if you can't get there, and then go to training data, and then we'll just draw some X's. Let's do like if everyone does like everyone just do like 3 or 4 X's and O's initially.
We have to sign up first to be able to input the test data, right?
No.
Oh my gosh, my O's are horrible.
Okay. So just let me know when you've got like.
Is this the next cookie clicker? Or Chad, are you going to be a billionaire?
It might be stupid enough to make money off of it. Okay, so I'm gonna assume people have done that. So I'm gonna go home and then I'm going to update the model. So I'm gonna create an account, which is going to be ASDF. I'll sign up. You'll have to excuse the UI here, and I'm gonna log in. And once I log in, then I should be able to update the model, and it gives me the estimated accuracy score, which is not too bad for small data. So now I'm gonna test it out, see if it works. So I'm gonna draw an X. You guys can also do the same thing. Probably drew an X. Let's see if I do an O. It gets an O. What if I just do some garbage? Thinks that's an X. So it's not perfect, and this is actually better than I thought initially. Okay, so that one doesn't do a good job. That's fine. That one does. Okay, so this is a very simple problem. So even with a relatively small sample set, it does pretty good, but we can train it some more. So I'm gonna go back. Let's provide training data, and everyone just do like a few more X's and O's.
I wonder if it's because I drew a tiny X, if now I need to draw a tiny O to get it to recognize those.
No, you can do whatever you want. I mean, it's you know, it's just it is what it is. Whatever data people give it.
I may have messed up your data set. I drew an X and clicked O. So
Yeah,
sorry about that.
it's fine. You know, this is one reason why you want to have lots of data, because data is going to get corrupted. There's going to be incomplete data. So part of that you want to handle when you're cleaning, but in this case we're kind of just accepting anything that anyone gives us. So
Why is
Doesn't the
this
model
so fun?
it really is. Doesn't the model also kind of look for outliers and kind of account for those too? So like if James did do that backwards, it's going to kind of realize that, right? In the
it could,
model.
so it'll be a very weak signal. So if you have like thousands of inputs, and they're all like very similar and one of them is different, it's not that it will necessarily exclude it, but it's just going to be lost.
You won't give it much weight. It
Yeah.
takes the weight away from it. Okay.
Okay, so I logged in. So I'm gonna update this. So better, it started like 60 something, now it's 80 something. So accuracy score you gotta take with a grain of salt, but and so if I test it out, I don't know if you guys, so an X, it's looking pretty robust. So that one we didn't get.
It does not like the O's.
Yeah. So it's obviously like over guessing on O's. So one thing you might do is provide it more data, just provide it more data and see how it does. But so this is usually with machine learning, you're not getting your data like on the fly like this. You definitely can, and there are lots of applications that do, but usually it's here's our data set, you pull it in, you process it, you clean it, you train the model, and that's kind of it. You can also iterate again as you get more data, but yeah, so that's basically it. If anyone has any, I'll stop the recording now, but if anyone has any